Okay, so let me share my screen. Okay, so thank you all for coming again. So today I want to talk a little bit about pavings. But again, this is joint with Martha Precup and Amber Russell. And so a paving, so that just, I don't recall if I defined this last time, so I think I did, but I'll just remind you that a paving of X will be a filtration X0 contained in X1, Xn is X, each Xi is closed, and Xi less Xi minus 1 is a disjoint union of C to the R modulo a finite group. Okay. And so these things that we're talking about today are unlike Springer fibers where you don't have to mod out by the finite group. You get what's real, a genuine affine paving is one where you don't have to mod out by the finite group. Now, this paving here is really just built out of the paving of the Springer fiber itself. So actually, in most of my talk today, I will just actually tell you some known results about the pavings of the Springer fibers, and I'll explain how you can get a paving of these things from that. So I won't recall at this instant the generalized Springer fiber. I'm just going to talk about regular Springer fibers for a moment. For more than a moment. So most of the talk is, or a good part of the talk, will be, pavings of Springer fibers. Now, before I actually even talk about pavings, I want to talk about the irreducible components of the Springer fiber, because this is kind of a warm-up to the paving thing, but I think it can be expressed in a way that's more transparent than when I start to talk about the pavings itself. So let me just explain the components of the Springer fibers, and that's going to lead us into Tableau, which are things that are going to index the pavings. But at that point, it becomes less intuitive where the Tableau come from. So I would like to just talk about the components where it's quite intuitive that you can see a Tableau. Although there's some things to prove that it actually, it does what I tell you. But so let me just make a definition. So let lambda be a partition. So what that means is a decreasing sequence of integer or non-increasing sequence of integers. You can think of this as being like the Jordan form. So for example, lambda equaling 4, 2, 2. And so then this, of course, corresponds, as I think most people are familiar with, to a diagram, Young diagram that looks like this. And then a standard Tableau, it's a filling. So we say lambda, just to back up for a second, lambda is a partition of n if the sum of the parts of lambda is n. So here, lambda is a partition of 8. So a standard Tableau is a filling of the boxes of lambda with integers 1 up to n. And a row strict tableau, oh, sorry, to back up for a second. It has to be increasing along rows and down columns. And a row strict tableau, you only require increasing along rows. So you could say the row strict RST of lambda, this is a set of row strict tableau. This would contain the set of standard tableau on lambda, right? I hope that notation is sort of clear. Row strict tableau contains standard tableau. And so the theorem, the first theorem, which I would probably attribute to Steinberg.
So the row strict is the same as
I'm not actually an expert on Tableau terminology, so I'm not sure if that's true.
The standard Tableau index of basis for the symmetrical representation corresponding to lambda.
Yes, that's right.
And the row strict ones correspond to the basis GLN representation.
I see. Yeah, well, I mean, the GLN representations are indexed by, highest weights, which I guess are Tableau, but you just they don't have to be positive. I mean, the GLN representations are.
So you're doing things with polynomial representation.
Yeah, let me not try and answer your question because I think I'm getting confused about it. So I don't want to increase my level of confusion at this point.
We can talk about that.
Yeah, maybe there's a certain point in one's talk when one can become confused, but 12 minutes into it is a little too early. Anyway, the theorem and I'm attributing it to Steinberg and Spaltenstein, is that the irreducible components of the Springer fiber corresponding to a nilpotent element in O lambda. So remember last time we said that the nilpotent orbits, and this is in type A, are indexed by the partitions. Their O lambda would therefore be a nilpotent orbit. The Springer fiber only depends on any on the orbit. If we take any nilpotent element and we look at the Springer fiber corresponding to a nilpotent element, they are in bijection with the standard Tableau shape lambda. Okay, and I actually think this is a beautiful fact, and so let me explain how this correspondence goes. Although you can imagine that there would be something to prove, and actually I'll tell you when I'll tell you something. It's actually there's actually something very elementary which is even unknown about this right now. So you can put your minds to that if you want. So here's how this works. So let's let n be a nilpotent element. And we identify X as the flag variety, it's the G mod B, and it's the set of all flags. We identify this with the set of all flags, E1 contained in E2, contained in E3, contained up to En. And the Springer fiber, remember last time we said that the Springer fiber, we have N tilde is G cross B of U, and this maps down to N. Here we have N, this is mu. We have mu inverse of N here. But in fact, we can map this down to G mod B, and this map, this projection here, pi takes mu inverse of n isomorphically onto its image. So we often identify the Springer fiber itself as a subset of G mod B. I think I said this last time. So xn, it's the image in X of mu inverse of n, and it's isomorphic to mu inverse of n itself. And so we identify this here, and this can be just identified as a set of all flags E dot, I'll call it a flag, such that if I take n and I apply it to EI, I'm contained in EI minus 1. And if we do that, we can see that this condition, of course, implies that n is nilpotent, because if you apply it a bunch of times, you're going to get down to 0. I mean, E0 is 0 here. Okay, so then the point is that how do I get a, so any flag in Xn has corresponds to some Tableau. And how do we do this? Well, we start off with E. So we look at we look at X restricted to E1. That has Jordan form. It's just one box here. So we label that box with a 1. Next, we look at X restricted to E2. Well, this has Jordan form with 2 boxes, because it's a dimension 2 thing. So there's 2 possibilities. Let's say that it has Jordan form that looks like this. We put a 2 in where we added the box. Then we look at X restricted to E3. Now it's a theorem. I mean, it's not completely obvious, but the Jordan form of X restricted to E3 is obtained by adding a box to the shape from E2. So that's actually a fact that has to be proved, right? It's not completely obvious that the Jordan form of E3 is that, but it's Steinberg proves that. In fact, he has this beautiful little paper called An Occurrence of the Robinson-Shenstedt Correspondence. And so there's only 2 possibilities. Let's say it's this possibility here. So then we would put our 3 in this box here, and so on. And so you can see as you go through the various Jordan forms of the flag, you're adding a box each time, and you just put a number in to record the order in which the box is placed in the Jordan forms, and you get it. Therefore, you get a Tableau. And then the theorem, and then what happens is that if you look at the closure so if you, sorry, let me back up for a second. So if sigma is a standard Tableau, you look at the closure of all flags so with this corresponding to this Tableau, which give you this Tableau. This is an irreducible component of Xn. And that's how you get all the irreducible components. Now here's something that is interesting, however. These components intersect. Suppose that E is in, say, a bunch of things. S, T is in this, the component, I'll call it the component corresponding to sigma, and it's also in the component corresponding to sigma prime. How do you know what Tableau is in the label of these 2 things? There's multiple possibilities. These components have a complicated intersection pattern. So I don't think it's really known a good way to describe, like, from this point of view, what the label that would be assigned in this way. So anyway, that I think is sort of interesting. But this is I think a rather beautiful fact. Now, this only deals with the irreducible components. And I think the way I've described it is kind of the way Steinberg describes it. And Spaltenstein has a slightly different description of things. And there's different conventions and so on you can take as well.
So this is a shadow of the Springer. Because, if you look at irreducible representations, basically it's by the standard number.
That's right. That's right. It's a shadow. That's exactly right. Because what happens is that there's an irreducible representation on the homology, and the classes of components provide a basis for that representation. That's correct. That's right. And so, in fact, what happens in this generalized Springer case is you see a similar shadow of the generalized Springer correspondence of Lustig. So that's so. Okay. Anyway, so now let me explain how you can do something a bit more complicated to get pavings. But maybe before I do this, I'm not sure what I'll get to at the end. So I mean, so just let me say that when one constructs a paving of the Springer fiber, if you look at it carefully enough, you can have the Springer fiber, and then there's the generalized Springer fiber, which is the inverse image of that. And the final step, which I'm not sure how much I'll get to today, is looking at the inverse image of that paving there. So we'll see how far we go today. But let me talk about the pavings of the. And so the way I'm going to talk about it is I want to give an exposition following a paper of Martha Prekup and Caleb G., who was her student actually, and he was actually an undergraduate student. And they have a paper where they describe a paving of the Springer fiber in a way that I think is very nice. They actually do this for Hessenberg in the more general setting of certain kinds of Hessenberg varieties. So I'll give a description of how you can, of a paving, or at least some of the ingredients of what they do for a paving. So the fact that the Springer fibers and these Hessenberg varieties are paved, I mean, the stuff I'm talking about from them, I wouldn't want to try and get all the attributions correct, because they were generalizing some work of Tomaszko. And Tomaszko's work, some of that had applied to Springer fibers, and their actual paper was generalizing this to certain kinds of Hessenberg varieties. So I think in the case of Springer fibers, much of what I'm going to say would be very closely related to what Tomaszko does too. And since this is just an algebra seminar talk, I'm not going to try and get all the attributions correct. But what I'm saying is drawn from the paper of G and Prekup. And I think what they did is, it's related, but I wouldn't want to try and say exactly how they're the same or different. But the basic idea is that, so again, we have our Springer fiber, Xn sits inside X, which is G mod B. Now G mod B is paved by the Schubert cells. I can take XW, the Schubert cell, and this is the orbit. It's U applied to the coset WB, and that's in X, which is U mod B. And these cells provide a paving of X. Now, the goal is we want to choose N in O lambda. So there's some choice of N. We can choose any representative, and we want to choose this such that the non-empty intersections X0W intersect Xn are a paving of Xn. Now, it's not at all obvious that you can actually do this. So it's actually, and maybe I'll just add this here. So this is following paper of G. So how do we do this? So first of all, I want to describe how we choose N. So basically, we take the Young diagram for lambda. So for example, let's just say we had, so say 3, 2, 2. And we fill this in with 1 up to n going up along columns and from left to right. So this here, we fill this in 1, 2, 3, 4, 5, 6, 7. Okay. And then what we do is we make a nilpotent, the nilpotent element n is basically, it's the sum of the elementary matrices where I look at adjacent boxes in this diagram, in this filling. So here 1 and 4 are next to each other. So I take the elementary matrix E14. 2 and 5 are next to each other, so I take E25. 3 and 6 are next to each other, I'll take E36, and I'll take E67. Okay. Now, what does this really mean? This is a kind of not very transparent way of looking at it, but here's what the matrix N does. If EI is the standard basis of C7, then what does N do? It takes the matrix E3 and it goes to 0. E6 goes to E3. E7 goes to E6. E2 goes to 0. And then E5 goes to E2. E1 goes to 0. And E4 goes to E1. So basically, that's, this, when we write it in terms of these elementary matrices, it's not completely transparent what it is. But when you do it this way, you see it's a very natural way of getting a nilpotent matrix. You're just telling what it's doing, and you force the Jordan form to be what it is, because you've just written down exactly basically a basis that it's in Jordan form. Okay, so that's the choice of n. Now, any permutation so they call this filling, by the way, they call this filling. They just give it a name. They call it RE. E is for the identity element here. It's not for. So any permutation W in Sn or S determines a filling of this Young diagram. And how do you do that? Well, again, it's a little bit not clear the best way to do this, but the way they set it up is, well, you'd think we put W1 of here. Well, in fact, it turns out you want to put W inverse of 1 here. So it's not completely clear you want to put W or W inverse, but in fact, you want to put W inverse of 1 here, and W inverse of 2 here, and etc. And so that's how you get a filling of this Young diagram. So any permutation then gives you a filling. And so there's an obvious bijection between permutations and fillings. So there's bijection. But the theorem is that, and maybe I'll say D precup, but maybe I'll write Tomas code here. I'm not exactly sure. Is that, so by the way, they give this filling a name too. They call this R of W. And the theorem is that the intersection xw naught intersect the Springer fiber xn is non-empty if and only if R of W is a row strict tableau. Okay, so in this case, if non-empty, it is isomorphic to CR, where R is the cardinality of the set of, I'll call it Springer inversions of W. So what is it? Let me just explain what that means a little bit. So here, the set of inversions of permutation, so the way they set it up, it's just convenient for them to do it in the opposite order. An inversion, they're going to say it's a pair K, comma L. Usually in the inversion thing, K is taken as to be less than L, but we can take K, it's basically K, where if K is bigger than L and WK is less than W of L. So this is not the usual definition of inversions. It's actually like it's actually basically inversions of W inverse, actually. So, but anyway, so I mean they've sort of labeled their things here by W inverse anyway. So I suppose it's not surprising that this is more like the usual W inverse. But anyway, the way, so what you can see here is that if we took up something like this, let me just take an example that looks like this. So the inversions of W in terms of the diagram, so it doesn't depend on lambda, but you can write it in terms of lambda anyway if you want to. In terms of lambda, it would be the set of all pairs K and L, where K is bigger than L and K comes before L in the filling order. By the filling order, remember, I mean you go up columns, then you go from left to right. So here, for example, so in this example, for example, it would be three come, if I'm going up, I see that 3 comes before 1, and 3 comes before 2, and 7 comes before 1, 7 comes before 2, 7 comes before 4, 7 comes before 5, and 7 comes before 6. And that's all the ones that we have. Okay. So that's the set of inversions, and then the Springer inversions is equal to the K of L in the regular inversions such that if there is a box to the right of L of the box containing L, with entry R, then K is less than or equal to R minus 1. So what happens here is that in this case, if we were going to circle or cross out the ones that didn't work, 3,1 is fine because 3 is less than or equal to 4 minus 1. And 3,2 is fine because 3 is less than or equal to 5 minus 1. But 7, the only way 7 can work out is is with a 7 and 6, because 7 is too big to be less than any of these other entries here. So the only ones that work out for these are the spring inversions, are just those three in this case, because there's no box to the right of 6, so that works out. But that's the general rule: is you look to the box of the right of the second thing, and it has to be, you know, bigger than the first thing in the pair. And so, in fact, so in fact, the cardinality of the inversion set is the dimension of the Schubert cell itself, and then the smaller thing is the cardinality of what happens when you intersect this with the Springer fiber. So you get a smaller vector space. And so that's the, yeah. Oh, with R is the entry to the right of this box here. So in this case, this 3, 1. So if we were looking at this 3, 1, so 3 is K, 1 is L, and R is 4, because R is the entry to the right of L. So it depends, R depends on what K and L are. Okay, is that clear? So if I took,
You also had another R. R was
another
also the
R
number.
is, okay. R prime. How about that? Sorry, it's sorry, different R.
If you change the R prime, you see R too.
Yeah, I sorry, I didn't harmonize my notation totally here. Okay, so any questions at this? Any other questions at this point? So this, I think, is a rather beautiful fact too, and actually, it's not at all obvious that this could be made to work actually, and it requires, you have to choose n in a very, smart way for this to work. If you chose n in a bad way, it wouldn't work.
So what's happening? So I see why your 3, 1, and 3, 2 are included, but what about 7, 6? Because there's no entry to the right of 6.
Right. So I said if there is a box, then k has to be less equal to r minus 1. If there's no box, then there's no condition. So that's right. That's if for the biggest entry, the only Springer inversions that could appear are ones where you get the last entry in a row for that reason. With this 7, that's the only possibility. The only possibilities that would occur, could be. Actually, I take it back. It looks but actually I did make a mistake. 7, 4 is actually also okay, because there's nothing to the right of 4 actually. So 7, 4 is actually allowed too. I should have. There's nothing to the right of 4. But 7, 5 isn't the correct, because the only things that could pair with 7 are things that are at the end of a row, because 7 is the biggest entry there. So 7 couldn't be less than anything. Okay. Any other questions? So now the thing is, you can calculate the dimension of these, and so what you can see is that then the standard Tableau are gonna, one would have to check this, but the standard Tableau are gonna be the ones where the biggest dimensions occur, and those would be the ones where you get the pieces corresponding to the irreducible components. So that would require some proof. I don't actually know if they even check that in their paper, but that's the way it has to work. Okay, so, but the way I've set this up, it's not exactly clear that I'm using the same, that this indexing is exactly the same as the one I did at the start of the paper. So one would need, again, there's all these kinds of conventions that one would have to check. And this one is a little bit less transparent than the one at the start of the talk. So that's why I wanted to mention that one. Okay, so then so what happens for the generalized Springer fiber? So let's just, to fix some notation here, remember we had this m tilde going over n tilde. We were going down to n here. I'm going to omit m because we actually don't need m in this picture. So I'm going to omit it for this talk. So we have this map here, which we called, maybe we call it psi. And so the Springer fiber here, we identified xn was identified with mu inverse of n. And then this is a union of cells, I'll say C sigma, where C sigma, where sigma is a row strict tableau shape lambda. Okay, and that's our paving of xn. So let's call this map here. Call it psi. So psi inverse of xn. I'll just give it a name. I'll call it xn tilde. It's not actually sitting inside the flag variety, unlike xn. Right? So I'm just going to give this a name here. And now the map psi is a finite map because it was constructed out of these torque varieties. So what we might hope is that each of these cells, there would be a finite union of these kinds of quasi-cells sitting over it. And that's exactly what happens, in fact. So I want to introduce something called, I'll call the divisor or the maximal divisor of a tableau. So let me just illustrate this with an example here. So consider the tableau. Okay, so consider the tableau. It looks like this. Now you observe, so if you look at this, what you see is that you can break this up. You can see that you can break this up into increasing strings. This is an increasing string. This is an increasing string. This is an increasing string. So you have a bunch of increasing strings like this. If you can break your tableau into a bunch of increasing strings of length d, we say that d is a divisor of the tableau. So if you can break your tableau, or divide your tableau into increasing strings, d, then d is the divisor of the tableau. And so let's let d sigma be the maximal divisor. Obviously, if 6 is a divisor, then 3 is a divisor too, the way I've defined it. So there's got to be there's a maximal divisor. So let d sigma be the maximal. And then the theorem is that the inverse image C inverse of C sigma is a disjoint union of, I'll call it C tilde sigma 1 up to C tilde C sigma D sigma, where each C tilde of sigma I is isomorphic to C. Well, I don't know if I should call it R or R prime now. Maybe I'll just call it S. modulo some finite group, which can be explicitly determined. And the center Z of G permutes the C tilde of sigma I transitively. So what you're sort of seeing here is the shadow of representations of smaller symmetric groups, where you because here you're starting off with a tableau. I mean, you could sort of imagine a divided tableau here, where you just sort of you took a tableau that would be like this, and then you just ordered by the orders of your blocks. So this would be something like 1, 2, 3, 4, 5, right? You can make a littler tableau like that by just looking at the orders of the various blocks. So the tableau with divisor, in this case, the tableau with divisor 2 would correspond to some kinds of representations of S5 instead of S10. And so what you're seeing is a kind of shadow of representations of smaller symmetric groups. And that's exactly what Lustig's generalized Springer correspondence does, is he assigns to, he looks at various representations of smaller symmetric groups, which are, instead of Sn, they're S of n over d. And out of these representations of S of n over d, he comes up with local systems on nilpotent orbits. So you're seeing this geometric shadow of these smaller representations, of smaller symmetric groups by these kinds of things here. And the action of the center corresponds with somehow the action of the center, which appears in Lustig's generalized Springer correspondence in type A. Somehow that basically the action of the center kind of determines it in type A. Okay, so that's the main theorem, and then these form a paving as well. So I won't use form a paving. Okay, are there any questions?
I have a question. I'm a little confused about this divisor. Do the strings have to be increasing by 1?
Yes, consecutive strings.
Consecutive. And are you only defining this for row standard tableaus? Or
Yeah, I mean, it's only relevant for, I guess I should have said for row strict Tableau, yeah, because we're building this out of the ones for, so maybe I should say let sigma in RST of lambda. I mean, one could define it for non-row strict tableaus, but the intersections with the regular Springer fiber themselves would be empty, so there would be, you wouldn't get anything out of this construction.
thanks.
Okay, so how would one prove this? So the basic idea is, and this is something that it comes from the way that G and Prekov construct their paving, and it's actually kind of nice in a way. So, but it's a little bit. So maybe I'll just sort of say. So the basic idea would be the following. So G and Prekov construct their paving as but basically they find a map of C. Now I don't know whether I should call this R or S, but I'll call this S now for right. They actually construct a map of CS into the group G, and then they map that into G mod B. So and then that's which is X. So in fact they're not actually just mapping into G mod B. They're actually constructing a map into G, and then they project it. So if one does this, you can use this to lift this to actually, if you have this to N here. So maybe I'll call this map. I'll just give it a name. I'll call it psi for the moment. If you have this to N, if you have N here, you really want to lift your map up to the actual N itself, because the generalized Springer fiber doesn't sit in the flag variety. So you have to work upstairs in the bigger spaces. So you have to sort of undo the identification that I was doing at the start of the talk and get back up to n instead of down to that. And so what you would do here is you just take some x here. And so the way their map goes here, if you mapped it all the way down to here, you would just go to the coset phi of x times b. And that's the way you get into the flag variety. But if you want to get into n itself, what you would do is you'd map into the, remember this is g cross b of u here. So you'd want to map this to phi of x, and then phi of x times your nilpotent element n here. Something like that. And when you do that, then, and there might be some, it's possible I may have to put some inverse in here, actually. Let me not try and get this 100% right here. But I mean, let me try and get this 100% right, but let's hope you can forgive me when I fail. So it's something like that. But there's this, you know, you can, that's how you would lift it, because then you end up automatically in the Springer fiber. And so what happens is that, so basically, in other words, what we get is a map from CS actually into U itself. And you remember that mapped into U mod U, which was this toric variety, which is our toric variety. Now, all that's interesting that's happening in the Springer fiber situation is happening in this map, in the extended Springer fibers, going from this map from V to V add. So the first thing we would want to do is we want to look at this image of the G and precup paving from CS into V add. And then we'd want to try and understand the image of that, the pre-image of that in V. And then that's basically going to, however many pre-images of that V add thing are in V, that's going to govern all of this stuff here is really governed by looking at the inverse image of this V add to V picture here. And so the basic fact here is that the image of the map CS to V add is easy to describe. G and precup. And how does that work? So VAD is just isomorphic to, remember, it's Cn minus 1. Because VAD was the stuff that was, we had our n by n matrices, and VAD was the stuff that was right above the diagonal in our n by n matrices. So it's isomorphic to Cn plus Cn minus 1. And this image, the image is defined by, so out of our Tableau sigma, we get 3 subsets of n minus 1. Now let me pick an imaginative name for them. I'll call them I sigma, J sigma, and K sigma. There are 3 subsets. And this can be just calculated by looking at the entries of the Tableau sigma, but I won't, let me not tell you the recipe at this exact instant. Maybe I will if we have a second at the end. And then the rule is that, let me just see if I can actually remember this or get this straight here. So if I take these subsets here, then what I get is I get the image is the subvariety, or the image is the subset of Cn minus 1 defined by the equations well, if I take xc is equal to, well, I'll say xj is equal to 1 for j in j sigma, and xk is equal to 0 for k in k sigma. So for example, if n was equal to 4 and our Tableau had something like I sigma equals 1, j sigma equals 3, and k sigma equals 2, right? So it's a subset of n. So n minus 1 is 3. So we have it divided into 3 parts. Then our image is defined by the equation, by just the equation x2 equals 0 and x3 equals 1. So in other words, the image is isomorphic to the set of all x1, 0, comma 1, sitting inside the set of just x1, x2, x3, and that's the add contained in, which is just C3, right? So that's what the image is here. Now sitting inside here, so now here we had V, and then up here, remember, if you, probably none of you remembers from last time, but we made another space here that was also isomorphic to C3. And this space in the middle here was our C3 modulo some somewhat mysterious finite group H. And then this map here is just the quotient by the center. So from V to V add is a quotient by the center, and this map here is a quotient by the group H. And so basically, if I call this map rho, basically what I have to do is I have to understand the inverse image of this component of the set. In this example, would just be of the subvariety defined by x1, 0, 1 contained in V. So what I can do, let's just call this composition here rho hat. So rho hat of the set of x1, 0, 1. What this is, there are actually going to be 4 components to this, because what they are is going to be, I'll just say z1, 0, 1, z1, 0. I can only put a 4th root of unity in here, because when I go down, the composition here is raising to the 4th power of each coordinate. So I can put I here, I can put z1, 0, minus 1. I could put z1, 0, minus I. Right, so if I go all the way up here, there are just 4 components. Because as I said, again, this map, if this has coordinates z1, z2, and z3 are coordinates here, the map from v hat to v hat is just raising each coordinate to the 4th power. So there's 4 inverse images here. To figure out rho inverse, of the set x1, 0, 1, I just have to figure out how many of these components are collapsed by the group H, which identifies some of the components. And so you can do that thoughtfully, and if you do that, what you see is that there are going to be d sigma components left, actually. The identifications work out so that they're actually d sigma components. So we just have to figure out how these components are identified by H. So I think in this case, there's like 2 components that survive, like 2 of these things map together. So I think what happens is, in fact, something like, if you look at the square of the last coordinate, that's the invariant that distinguishes which two things they map to. So 1 and -1 map to a different thing than I and minus I in this middle term there. But this is also, but because everything is so explicit with just finite abelian groups and toric varieties, this can all be calculated very explicitly. And so it's actually a very concrete calculation at the end, and it really just boils down to this toric variety thing combined with the Springer fiber results themselves. So that's all I wanted to say today. So thank you.
Just for the sake of the recording, I think the thing that has 4 components is rho hat inverse of that set.
Yes, you're right. Thank you. That's rho hat inverse here. Thank you. That's what I meant to say. Sorry. But you can see what's going to happen is you always get a picture like this where you get ones, zeros, and variables in your variety. And then you go all the way up to the top. Every time you have a 0, that doesn't do any, you don't get anything new. Anytime you have a 1, you get a Zn choice of parameters up there. Anytime you have a variable, you just get a variable up there. And so you just have to look at what how these Zn parameters get permuted by H. Okay, so I think I will stop sharing my screen now.
You might have said this, Bill, but I missed it. Did the I sigma, J sigma, and K sigma form a partition of n minus 1?
Yes.
Okay.
Yeah, I didn't say that. I just said they're subsets. But yeah, it's basically depending on where they lie and where the other entries are relative to them. I think J sigma is all the consecutive strings here. So here J sigma is all the ones where the entry to the I plus 1 lies immediately to the right of it. So here's something like J sigma would be, I think, 1, 3, 5, 7, and 9, because those are all the entries where the next +1 entry lies to the right of it. And then I sigma is defined by something a little bit more complicated, and then K sigma is just everything that's left. So it's very concrete to read it off the Tableau. Okay, any other? Okay, well, thank you all.
Okay, so let's see.